Welcome back to the Datarekha audio guide. I'm Diya.
And I'm Arjun. Today, the exact moment every LangGraph developer grows up, when they discover their perfectly working chatbot has the memory of a goldfish and learn the one feature that fixes it.
Paint me that moment. What goes wrong?
It works beautifully in development. You ship it. A user sends 3 messages, gets great replies, closes the tab, comes back an hour later and asks, "What did I just ask you about?" And the agent has absolutely no idea. 2 things conspired. The pod that handled those first 3 turns got recycled. And even if it hadn't, the in-memory state vanished the instant the call returned.
So it's worse than the server restarted. Even on a perfectly healthy server, the memory was never going to survive past a single run.
Exactly. A compiled LangGraph runs once and forgets everything. That's fine for a demo. It is not how production agents work. And the fix for all of it is one feature with a slightly intimidating name: checkpointers.
Okay, demystify it. What does a checkpointer actually do?
It's a durable store that saves the full graph state after every single node runs. Every step, it writes a snapshot. So instead of state living only inside the process, it lives in a database that outlasts the process. And once state survives outside the process, the graph gains a superpower. It can stop mid-run and be resumed later, from a different process, a different pod, even hours later.
And I'd bet that one property, stop and resume, quietly buys you a whole pile of features that sound unrelated.
It really does. 4 big ones, all from that one idea. Multi-turn conversations. Turn 3 sees turns 1 and 2. Resumability. Process dies mid-run. You don't lose anything. Time travel debugging. Something breaks on turn 17. You go inspect the state at turn 12 and rerun from there. And human-in-the-loop pauses. Stop the graph. Walk away. A human approves something. Resume. All 4 are just stop and resume wearing different hats.
Let's get concrete on multi-turn because that's the everyday one. How does turn 3 actually know about turn 1?
Through a thing called a thread ID. When you compile the graph with a checkpointer, every call needs a config carrying a thread underscore ID. The thread ID names a conversation. All the state for that conversation gets stored under that key. Same thread underscore ID on your second call. The graph reads back the state from the first. Different thread underscore ID. Totally fresh conversation. That is the entire multi-turn API.
So let me make sure I'm not overcomplicating this. There's no chat loop class, no session manager object. The whole thing is state keyed by a thread ID and you pass the same ID back.
That's it. That's the whole pattern. In a chat app, the thread ID is usually just your conversation ID. In a long-running job, it might be the job ID. It's nothing more than LangGraph's way of knowing this is the same conversation. Go find its history.
Now the name thread is a little dangerous. People are going to assume it spins up an OS thread, a separate CPU thread.
And that's the trap. It has nothing to do with threads of execution. It's purely a storage key. Think of it like a labeled folder in a filing cabinet. The label is the thread ID. The folder holds every snapshot of that conversation in order. A new call doesn't run in a separate thread. It just opens the right folder and reads the latest page.
That folder framing also makes time travel obvious. If every step is its own page in the folder, debugging is just flipping back a few pages.
Exactly right. The compiled graph gives you the history of every checkpoint, newest first. So you grab the snapshot from 5 steps ago and re-invoke from its config. Each checkpoint carries an ID you can branch from. That's literally how rerun from turn 12 with a different message works. You iterate on one broken step without replaying the entire conversation. When you're debugging turn 17, that is gold.
There's another method I've seen, the one where you patch state from outside the graph entirely.
Update state. Say a human edits a draft the agent wrote. You can reach in and modify the saved state directly without running a node. But notice, That only works because there's a checkpointer holding a saved state to patch. No checkpointer, no saved state, nothing to update.
Let me switch to the user-facing side. When I talk to one of these agents, I see thinking, then searching docs, then drafting. The plain call just blocks until it's all done. So how do I get those intermediate beats?
You switch from invoke to stream. Invoke runs the graph to completion and hands you the final state. One lump at the end. Stream yields each intermediate update as the graph moves through nodes. So as the agent finishes the retrieve node, you get an event. Finishes the draft node, another event. That's exactly how you light up searching. Drafting. In the UI in real time. Same graph. You just consume it as a live stream instead of waiting for the lump.
Now the practical side. What's the swap-in story across environments? I don't want to be running a heavy database on my laptop.
And you don't have to. And this is one of LangGraph's nicest design choices. Develop with the in-memory saver. Fast, zero setup, easy to inspect. Graduate to a Sclide-backed saver for local demos and pilots. Use a Postgres-backed one in production. Same interface, identical behavior. The only thing that changes is one argument at compile time. Persistence becomes a deployment detail, not a code detail.
That's clean, but write a checkpoint after every node makes me a little nervous about cost. What bites teams in production?
A few things, and they're worth naming. First, write latency. Every node writes a checkpoint. So a 10-node graph talking to a Postgres on the other side of the country is 10 round trips. Use pooling, keep the database regional. Second, state size. A checkpoint holds the full state. So if you're lugging around huge retrieve documents or endless message history, storage and serialization costs explode. Trim it. Third, schema evolution. State gets serialized. So if you change the shape of your state dict, old checkpoints may refuse to load cleanly. Version it, write a migration before you change it. And fourth, threads pile up forever by default. So plan a cleanup job or they'll bury you.
And there's a security angle hiding in here, isn't there? If the thread ID is the key to a user's entire history.
That's the one I tattoo on people. The thread ID unlocks all the state for a conversation. If a user can guess or count up through them, thread 1, thread 2, thread 3, they can read someone else's history. So generate thread ID server-side with real randomness. A UID is fine. Bind each one to the authenticated user. And never, ever accept an arbitrary thread ID handed to you by the client.
So the one sentence takeaway?
Persistence is the whole story. Compile with a checkpointer. Key everything by thread_ID. And you've turned a forgetful one-shot graph into a resumable, multi-turn, debuggable agent. Everything else is just deciding which database holds the snapshots.
Give your agent a memory and a folder to keep it in. That's the Datarekha audio guide. See you in the next one.